Hi everyone. So today we're presenting our capstone project that we've done with Puget Sound Energy on transmission hosting capacity. Me and my teammates Sam, Eric, Steven, and Manili have worked on this for 2 quarters, and here's a presentation. So let's jump to the problem statement. So uh, PSC is trying to determine the transmission system hosting capacity to study the interconnection of generation and energy storage resources at two levels of voltage, 115 and 230 kilovolts. PSC has a goal to fully transition to renewable energy by 2045. So in order to meet these goals, there is going to be an increase in the load and demand, which is due to the electrification of the grid. Thus, there's a resulting need for us to determine points of interconnection in the transmission system that can now support these new generation resources. So for anyone who's not from electrical engineering background, system hosting capacity can be defined as a level of generation that a transmission system can accommodate without causing thermal overload or voltage values. So we've implemented this using the PowerWorld software. So we got a list of transmission system buses from PSC and we determined the main elements from it. We ran ATC on PowerWorld for 4 cases, high summer, high winter for year 1 and year 5. We then checked this with PowerFlow, which runs on a Newton Raphson method to check accuracy for ATC. After getting all of the data, we prepared an Excel sheet that has all of the data in one place and created a resulting map on Google Earth using color codes for power developers to determine where they deploy their new energy storage resources. Now I'll pass on to Steven to talk more about the PowerWorld.
All right. Hello. So before we go on, we should talk a little bit about the software we were using. It's called PowerWorld. It's the power flow analyzer for Puget Sound Energy. It's proprietary software. And in addition to all of its usual capabilities in solving the power flow equations, it also has this tool or add-on called ATC, or Available Transfer Capability, that basically allows you to designate a seller bus, any bus in the PSE system, and a buyer, in this case, the entire Northwest region, just for this study. And this tool will automatically tell you what the maximum power injectable at that bus is without causing any thermal overloads or voltage instabilities, mostly thermal overloads. It'll tell you the worst case scenario. I'll tell you that transfer limit, the limiting element, and if you include contingency analysis, it'll tell you which contingency is causing this worst case scenario.
Okay. So in terms of requirements and objectives for our capstone project, first and foremost, want to have our transmission map be publicly presentable online for PSC to have on display once completed. And what this means is to make sure it doesn't have any sort of sensitive information that could cause any security risk whatsoever. And that includes not having exact numerical values, on the map. Instead, we'd rather have ranges of power transfer capacity instead. Additionally, we also want to make sure our map will assist potential developers and independent power producers that collaborate with PSC in the future to be able to properly determine points of interconnection within PSC's transmission system for renewable energy sources. We also want to include layers for the base case and the two contingencies, as well as for the weather scenarios that we deal with, such as heavy winter or heavy summer, both either 1 year out in the future or 5 years out in the future. We also want to have a methodology provided to PSC that will be along with documentation that details, how to properly update the transmission map. And one sort of stretch goal that we have is to introduce some form of automation of this entire process of updating the map, as well as performing power road calculations and simulations, just to speed up the process and make it a lot more concise and straightforward. This will be done with some form of Python scripting.
So we can do all this ATC calculation by hand, or run it by hand and then make the map by hand. But really, what we want to be able to do is automate this whole process, because as soon as anyone connects to the bus, any seller, that the map is going to be outdated, at least at the bus they're connecting to, but probably the whole system, because the dynamics of the power flow will change. So what we really want to do is make a script using Python's simulator auto add-on, just a Python script that will run through the ATC for every single major bus in the system, create the map pins, and then you can load it into a Google Earth file, or you can send it to the GIS guys to figure out how to make a prettier map. So that's what we did. We now have a script that uses the SimAuto add-on to run base case n-1 and n-1 contingencies. And the benefit of this is, although it's technically slower than if you did it by hand, you don't have to be standing there. You can just let the script run and it will go. And the last few problems we had with it is that it transfers unpredictably because of the issue we had with our laptops being disconnected from the internet and USB blocked for safety purposes, security purposes. And there's also a way to make PowerWorld use multiple cores to make the calculation as a whole faster, because some of the Puget Sound Energy employees are looking at 17 cases and n-1 contingencies. So we really also want to make it run faster in addition. So that's something we would do in future, or if PSE wants to run with this script, they can implement that as well.
So a little more about the map. The map is not going to display the actual transfer capacity as a number. That would fall foul of WEC, the committee that overruns the Western Grid. They don't want that kind of detailed information available to the public. So we create the map in Google Earth using pins to show all the substations that are of interest to us. And Google Earth lets us use multiple files, and they can be toggled on and off on the map. This means that we can create all the different layers for the different summer and winter loading situations and the number of years out in the projection, so that the map can be dynamic and we can show what we want to show. Our Python script is configured to automate the process of updating the map through the KML and KMZ files, and this is in hopes that PSE can use a lot less labor to update it than we had to actually just make it by hand the first time. And in that note, Sam is going to go into a little bit more detail about our map and the process of dealing with these KML and KMZ files.
The KML file format, which was originally designed for use in Google Earth, was chosen after we consulted with the PSE mapping team. So we created a template file in KML. This has all these substations in it. We sorted it out by county. And then any unused substations, such as the smaller minor ones that we're not using on the map currently, are placed into a folder that's unused. That way, if the team wants to expand the map or change it up later, they can just drag the relevant substation into the county where it needs to go. And then when someone runs the tool, they can either run all the counties at once, or they can just choose a particular county. In this example, we have Thurston County, and it's in the n-1 conditions. So go through, gets the data from PowerWorld, and then based on a map legend that's been chosen, it'll change the color of each of the pins and update them. And here's the initial map legend that we chose, the color ranges. Each one shows a number of megawatts that's within that range. But the team can also come in and change that pretty easily. They can remove lines if they want fewer ranges. They can change the limits of each range. And they can even update and change the icon that's going to show up on the map. And here we have the map itself for all counties. This is the base case. As you see, there's a lot of purple, which means there's 600 or more megawatts available there. There's not too much red except for up here. I also left in some error markers, such as this one right here. This is just kind of alerts the team if they have a mismatch between the substations that it's expecting to see and the substations they're putting into the code. So it kind of helps them spot if anything went wrong. And then also we can easily swap between that and like another map, such as this, which is the N-1 conditions. As you can see, there's a lot more red. So there's less hosting capacity when something goes down, and that will help the developers decide where they want to build.
To sum it up, we hope that PSE will be able to use the map and data we created to guide some of their future endeavors. And specifically, we hope that it's going to be able to be shared with the public so that developers will be able to use it to guide their decisions to find the areas that are best suited to develop green energy and are the most profitable. And we also hope that PSE can use it to find places in their system where they might be able to upgrade their capacity. Thanks again for listening to our presentation.